this morning. Welcome to the both CSD and SSD. It's an unusual day and time for both of us. Today we have a special guest, Professor Osaki, Professor of Research, Faculty, Agricultural University, Agriculture, Hokkaido University, and Professor, Graduate School of Agriculture at Hokkaido as well. He studies wetland and peatland, a lot of work with greenhouse gas emissions, removals, carbon sequestration, wildfire, rehabilitation, conservation in ecosystems. His expertise extends globally to sustainability study on climate change and carbon management in ecosystems. I see here he spent a couple of years in the 80s at CIMMYT in Mexico, so he's not an entire stranger to the CG system. And he's going to talk to us today about a research network that he's developed. I think many of us will be familiar with the areas he's talking about. He's talking about several of the mega deltas where Erie does a lot of work. So with that.
Thank you very much. So we three, the Professor Kishima and Nakatani and I have something, the mission, which is established the education system collaboration with Hokkaido University and ERI. And yesterday we discussing about this collaboration or make alliance. And so today, another the obligation for me to developing some the collaboration, the study, especially the ERI. And so my basic is the soil science and plant nutrition, not the GIS or satellite. So we are normally studying the field or the ground basis. And so we have a lot of the international project, and so we are developing the system to estimate the ecological system in the terrestrial or ground truth. And so on this the program, so we developing how to apply the GIS technology into the terrestrial ecosystems. And so the last 3 years, 4 years, we are developing the new innovative technology to estimate the ground truth. And so I introduced these systems, and so then after that, if you have interest, we make something collaborations, ERI or some other. And so we are targeting because of the Japan have a lot of the study, the paddy field, and which including the wetland and the peatland. And so we have many projects, and so now we are very interested about make something the network or collaboration the system with the tropical countries. And because you see this is I pick up the delta from the world, and so almost 16 the big deltas that are located in the world. And so you see this is the tropical zone and subtropical zones. How many the big deltas are located in the tropicals, including the subtropicals? So 75% big deltas located in the tropical areas. You know that delta is a very fertile soil, and so why the populations. And so now you see in tropical delta the affected climate change, the high tide and sometimes the dry and the flooding and so on. And so this is the common issues in the tropical areas. And so we are now how to developing the estimation, this kind of the environment or ecology or high human population, which is affect to environment. And so until now, so very few technology to estimate this kind of the total ecosystems. And so okay, so just we are focusing the tropical delta And so we try to establish to research or capacity building in the tropical delta areas, which called the TDL, and tropical delta network. And so to establish the network, you know, normally so already they have lot of the network and the collaboration, but we propose something new, innovative technology to sharing the idea of technology among in the tropical delta areas. And so the key technology is we developed the liquid crystal tunable filters. So later I'm talking about more details. So which is the hyperspectral sensors, and very small hyperspectral sensor like this. And so in the past, to apply the hyperspectrals, so the machine is required, and even only 1 point estimation, the instrument we must bring to the field, and so very hard work. But now, so we also developed only 1 point spectral estimations like this, like a pencils. And so then, so just the spectral sensors can load to UAV, unmanned air vehicle or helicopters, and so microsatellite. And so this is something the innovative technology. So could you remind this LCT, liquid crystal tunable filters? Very nice the sensors, the hyper sensors. And also we are developing real-time monitoring system in the ground truth. And also we are developing now, so if applied just a hyper sensor, huge data come down. And so how to analysis and how to binding the basic data. And so we are developing also the metadata analysis systems. And so this is technologies. And so this technology, how to apply actually the ecosystem or some other countries to conserve or to estimate the sustainability of the ecosystem in the global. And so why we are targeting the tropical subtropical zone? And so the issues, there are a lot of the issues in the tropical subtropical zones. And so one already I pointed out, delta. There's so many 75% big deltas located in tropicals. And so you know the delta is a high population, high soil fertilities, high population, and affected by the human impact and the climate change impact. So another is a very high biodiversity zones. For example, the Borneo, the Hias, and Amazon, and the mountain areas of Southeast Asia, like the hillside of the Himalaya mountain. And also, you know, in this tropical zone, we can find high carbon reservoir ecosystems, which is the tropical peatland, and the mangrove, and the coral. So this is the key ecosystem for mitigation or adaptation, the program under the climate change. And so the UNFCCC, they also now pointed out the key ecosystem to conserve and for the research. And so this high carbon reservoirs, the main big high carbon reservoirs that exist in, for example, the Central Africas, Southeast Asia, and Amazon. And another is, you know, already know the natural disaster. Philippines now affected the typhoon or so, hurricane or so. And also here, the Southeast Asia, especially what they say, this area drive both on the climate change, the very hot waters and the the transpirations, evaporations, and make big cloud and make a typhoon or storm. And this is also the point for the climate change itself, how to estimate the climate change here. And so, you know, this is the very important, the belt or zone for the climate and the ecologies and the environment, but very difficult to estimate these areas. You know, here is the very complicated systems. We say the human ecology environment hyperlinkage and the systems. And so how to analysis this kind of the complicated systems. And so second one is, you know, we want to apply the GIS, how to get the satellite data, but normally the cloud, covered with the cloud. And it's very difficult to get the data. And how to get the data, and so now we are proposing microsatellite or UAV system to get actually for real-time the monitoring systems. And so maybe third one is related to second one. So very few studied about wetland, peatland, coastal ecosystems, and including the tropical ecosystem itself. So now we are proposing some kind of the big international network. Still discussing, and at first we try to focus on the Mekong Delta areas, including the water catchment. And so then how to access this kind of the key issues. And so this is the hyperspectral sensor. This is the big satellite, planned by or designed by the Japanese government, Minister of Technology, but not yet launched. But we tested this, what they say, the sensor using the airborne, the systems, the similar the sensors we tested. And so this history, the sensor have 185 bands. So huge number of the bands history have. And so you see now normally we use the Landsat 8, and so only 10 the band available. And so missing the several band even the Landsat 8. And so this is only the picture of the pan-coronary. And so the visual band like the Landsat. And if apply the history, the sensors, hypersensors, so the analysis, the more what to say, we can get more information, almost the 100 times, sometimes 10,000, 1,000 the information we can get compared to the pan-coronal or something the visual sensor. And so this is developed the LCTA. Also the liquid crystal tunable filters. And so this is very small, the sensor put into the cameras, and this kind of the size, very small, and we can bring the field and take pictures. And if we know the something growth stages, something the tolerance, or if you want to select some materials, and so they take pictures, and you can get the information, physiological information, even in the ground. And so this is the system, very the complicated, simple the systems, and total is only the 6.3 kilograms. So easy to the UAV or microsatellite also. And so the wavelengths, this is the first model, and so now we have until 1,000 nanometers. And so And this is how many around 600 band we have. 600. Oh, I forgot to write it. The 600 band analysis. And so just the sensor tested in the UAV in the Indonesia, and so this is actual data. And so the 1 pixel is the 3 meters, the resolution. And so in the tropical, so you see the 3 meter is enough to estimate only 1 trees. So this one dot showing the 1 trees. And so different color showing the different species. And so this is the very unique the technologies. Until now, so no technology to differentiate the species. Only the primary forestry or secondary forestry, grass or so on. But now, so if applied this technology, we can identify each species of the forest, and not only forest, grass, and the crop also. And so this is the LCTF. Another is history the sensors, the airborne, the systems. And so this is the result. And so the 1 dot showing the 1 trees, so you see if applied this LCTF technology or hypersensor technology, we can find the biodiversity. 1 tree mapping is easy. And so this is the 1 year's interval. We take the pictures in the same areas, and we binding both data, and we found the forest degradation. And yellow is degrading, and red one color is not so clear. Red one is already dead. So you see only the 1 year's difference, we can find the forest degradation and the dead forestry or so. The REDD, the reduction emission, deforestation, forest reduction, which is very important now, the carbon, the issues of carbon credit. But how to estimate forest degradations? No technology until now. And only our technology available for this, the REDD plus. And so the biomass mapping, normally the high biomass and saturated the biomass estimation. But if the separated each species, and we apply the algorithm, allometries of each species, and so we found no saturated until I don't know what more than 100 kilograms, 100 ton per hectare the biomass, no saturated. And so another is available for estimate the deep water potentials. And so easy to map the deep water potentials using hypersensors. And another is this is the estimate the organic carbon in the peatland, in the river. And so the difficult this is a small, but you see actually we can estimate the high concentration of the organic carbon using this kind of the airborne. And this is the rice growth stages. And so in Indonesia, so several varieties mix, so but easy to estimate the rice growth stages. And so this is a rice yield mapping. And so in the past, normally to estimate the biomass or yield, and we use the leaf area. But the leaf area saturated soon, and how to estimate more than saturated leaf areas. And so apply the hypersensors. So we can estimate easy to the crop yield. This picture take the flowering time. And so after that, so we harvest it and make a correlation, and we found something, a good correlation, the yield and the hypersensor spectrums. And so this is the disease mapping, the rice blast, very important, the disease. And so in the past, the Landsat data are almost impossible to estimate this disease. But apply the hypersensor, this red one showing the high infected, and so if monitoring this disease, and so if some areas start to affected by the rice blast, and so we apply some chemical ozone, control more easy. No need to spray the chemical all over there. So you see, this is only a field example to estimate environment using the hypersensors. And so if you good ideas, so we can provide this kind of the data, and so the collaboration, we are developing the new world, new science. And so I say that the clouded is very the important issues in tropical areas. And very few the data that we can get from the GIS. And if, okay, so the clouded, but if we launch the several microsatellite, and so, for example, we just calculate 10 microsatellite in the equatorial orbitals, and 10 minutes interval we can get, if bind 10 the satellite, and so we can get the 10 minutes, theoretically, the pictures. Then so you see that even in tropical, in the morning or some areas, not so crowded, and we can bind in all data. And so even in the crowded, but we can find some the information from the tropical zone. This is the one ideas using the microsatellite. And so we already launched this LCTF by microsatellite. Just up now, so we are testing the machine, and so this is only LDVI the mappings. And so the LDVI, you see the only 2 band we use. And so this, the microsatellite, we call the Rising 2, and compared to the Landsat 8, so resolution is drastically improved. And so this resolution is 5 meters. And so even in the, what you say, only 2 band, and so we can get high resolution in LDVI. So dark is a very high LDVI. And so maybe something correlation with the growth. But if apply the more high number of the spectrums, and even in the dark or the high, and so we can find more clearly which is more the 5 ton or 6 ton, more clearly to estimate the high level of the yield. And so not only the satellite, we are developing the monitoring system in the ground. So we put several sensors. This is a combined compact sensors, and the data sent by the internet. And so the stock data. And so this is the case of the Indonesia in the wetland jungles, and we can access the data from the Hokkaido University, or we make a collaborate, or United States or here, so everywhere we can access. And normally, you know, the system developing in the world, a lot of the system, but maintenance and the cost is very high, but this is very cheap. And so this system now operated in Indonesia, and the government, Indonesia government, applied this system. And so the coastal areas, so subsidence is very serious, sometimes the high tide. And so we're estimating the subsidence of the peak. This is what they say, Stora is very, what they say, soft and so easy to subsidize. And we are developing this kind of system in the Southeast Asia. And so another system to estimate the carbon dioxide in the haze, and another estimate the thunder. This is very related to climate change. So this is also the simple system, and we also developing. And so this is the first ideas to how to binding the ground truth data and the satellite, and for estimating the peat, the ecosystems, and using the system, we success estimate what to say the peat depths using satellite, and so and the CO2 emission from the peat using the satellite. We are developing the several models, and today I have no time, so we'll be skip this result. But the binding the ground truth and the several satellite data and easy to estimate or make a model the CO2 emission and probably the methane emissions. And so in the past, we have used a lot of satellite data, and very difficult to binding. You know already the resolution date is different and very difficult to bind. But anyway, we success because of the lot of the monitoring data. And so now, so if we if you use the micro satellite, more easy to estimate the ground truth, the date, how to estimate ground truth. And so now some another the satellite, if binding the GOSAT, this is the estimated CO2 concentration in the atmospheres, and the GOSAT-2 now is available. And another is the pulsar, this is a radar, and the pass through the cloud, and so and also this high resolution now so easy to estimate the biomass, and some of the scientists try to estimate the biomass of the rice, and also some another the methodology is available, and if binding the microsatellite, so in future more easy to estimate ecological environment system, even in the very complicated wetland. Also, how to binding the metadata, and so another group now developing the huge sensing data, how to estimate the environment, ecological systems in some areas, and so they are correct something theory, visualize, and so application of satellite data, and so the mining data and binding together, and so estimate the economic, the impact under the climate change, or so on. And so the total system, if was established, is okay. Then so you know that I said the technology innovation using this LCTF, and if success estimate the globally, especially tropical areas, and so we provide data and which is contribute to something social, the policy decision or so on. And this is something new. the social innovation system. And so thank you very much. Also, you know, the Future Earth now starting from the last years. Our members also joined it, and we are trying to put the system into this Future Earth. And so I forgot one point. Okay, so this is now the only ideas, but you know already we launched one satellite, and coming 2 years, the Hokkaido University will launch 2 satellite modes, and 3 we will be operating. And last years, the Philippine government decided to 2 satellite launch using our system, Hokkaido University systems. And already we made a contract. And maybe so next year, you can available these data. And so maybe so this is the estimation disaster was on, but also this data is available to evaluate the environment for ecological. And so if you have interest, and we make a contract with IRI and the Philippine government and Hokkaido University, and we developing the estimation system. This is something start point of the international network. So if you're interested, we discuss and developing this kind of key network. Thank you very much.
Thank you very much, Professor Osaki. We have time for questions.
I'm just curious, how much does one microsatellite cost?
So
Because you have 10.
that is something depend on the condition. We contract with Philippine government. The government agreed to pay the 10 million US dollars for 2 satellites, but very cheap.
Very cheap.
Do you anticipate that the data will be freely available to institutes working in the region?
And okay, so we established this network, and we as much as possible to free. But now, so you know, just establishing these systems, and so we what to say to make a contract for the scientific purpose, so we can distribute. But in future, I don't know put some small cost or something. But until now, the free.
Thanks for the seminar. It's interesting. So you really piqued my interest with the disease, the blast example. So I wasn't clear, was that satellite or was that UAV that you used to do that detection? And does it only detect blast, or can you detect anything else and differentiate between diseases?
Okay, so the rice blast, this is a testing, so rice blast is very clear and so easy to estimate. And so we, you know, at first what they say, estimate the rice blast, we need the library of the spectrum. We take the spectrum on the ground, and which is affected the rice blast. And some another disease, we make up the spectrums. If change the spectrums, or we can differentiate it another disease also. We need the field test.
So the idea is that you have some kind of a database of the different what do you call that, waves or frequency, and then you match it with the corresponding disease. Is that how you do it?
Yeah, in the world, so already several libraries of the hyperspectrums, some available. And but you know the more the detailed analysis of the yield or disease, and so you must make own the spectrographer. But that is very easy now. So you can take the pictures, and so the what they say, the frequency of the something disease or some the symptoms, and so easy to analysis. Understand?
You mentioned, okay, there are two issues, because I'm thinking about here with making this into something that goes from research to more monitoring operationally. UAVs as a solution to the cloud cover problem. Are you looking at the different legislation or the laws in different countries about flying these kind of UAVs? Well, I mean, are there obstacles there that would make that difficult? And I'm very curious about the microsatellite constellation. And yeah, you see this happening now quite a lot. Even private companies becoming very interested in this concept. Low cost, $10 million low cost satellites, which are relatively low cost to other platforms which can cost 100 million plus. So this constellation concept, it's exciting. However, we do a lot of work in Southeast Asia in particular, in these deltas, and even just by looking at weather satellites, which take images every 15 minutes, you know, geostationary satellites, so you see the cloud systems.
Yeah.
My concern with a 10-minute interval monitoring is that you'll get 10-minute images of clouds at certain times of year. Even with 10-minute interval, it can be very, very difficult to get a cloud-free image, because those systems are so big and last such a long time that I'm wondering how you could try to link satellite-based observation with what's going on the ground or near ground. So I'm thinking about the integration of satellite, airborne, and ground systems into a system. I think you mentioned that at the end, but I'm interested about your thoughts on that, plus the UAV issue of legislation and law.
Okay, so UAV, you know already there are a lot of the regulation in each the government, and so we must negotiate. Even in the Indonesia, we negotiated the army or so on, so they agree, and so we fly. And so this UAV is something we limit to use, and so far that we are developing the microsatellite. This is no regulations. And so we targeting the 5-meter resolutions, but that is easy to make 1-meter resolution or so on. But you know this is the military issues will come, so very strict to something use this satellite. This is open, but still there's something pressure to use this. So why do we choose the 5-meter resolutions? So this 5-meter is no problem to use. So the second question.
About
Okay, ground truth.
integrating across different monitoring systems.
For example, how to binding the monitoring and ground satellite sensing and ground truth. This is one example which have done in the Drilon, Indonesia. And so the we developing the model to estimate the peak depths. You know that is the underground issues event, and so normally you see the satellite difficult to estimate the depths, and so this is the ideas. And so you see this is the shallow peak, and so this is the peak, the deep peak, and so we found from the monitoring. So in the deep peak, so water levels drastically changing, the wet season and dry season, and so if change the water tables, and so the physiology or phenology will be changed. Response is changing, and so the deep peak, so water level change very small even in the dry season and the wet season, and so no change the phenologies, and we have to estimate the phenology changing if drastically change the phenology, which is very shallow, and so also change the phenology, and so we make some data. We use the satellite, and so the binding actually we estimate the peak depths, several pointed. Then so using these models, we make a map like this, and so we multiple the carbon concentration. We can estimate carbon stock in the peatland using satellite data. This kind of the monitoring and what is the satellite sensing very important. After establishing these models, so we can estimate the peak depths only using a satellite. And some others are the case. So the CO2 emissions, how to estimate the CO2 emission, the peatland, by using this kind of monitoring and satellite sensing. This is the one case. And we monitoring a lot for a long time, most 10 years. And this is the water. I'm sorry. This is the CO2 emission. And so this is the what to say, the natural forestries and peat drained forestry and bound areas. And so CO2 emission is different. And so in the dry season, the CO2 emission is very high. And so regression is like this. The water level is decreasing in the dry season, and the CO2 emission is increasing. And we found this coefficient. Then so we developed the how to estimate the water tables. If we can estimate water tables in satellite, then so we can make a map. And so this is actually okay, blue line is actually we are monitoring long times. And so we make the models using satellite data and put the data into tuning in these models, and we calculate or estimate the water levels using satellite data. And so fitting is very nice. And so then so we can use the models and apply to some areas for using by using the satellite data, sensing data. This is the water levels mapping. And so you know that I say already the water levels and the CO2 emission have a linear correlations. And we put this data and we can estimate CO2 emissions like this. Each month we can estimate the CO2 emission. Not so clear, the sound. Yeah, it's clear, but the picture is not so. You see, the season is very high, the CO2 emission. This is just only using the satellite data. So you know the satellite data and the monitoring data, and we develop the models. And after that, so only using satellite data, we can, in this case, the pit depths and the CO2 emission easy to make a map. Okay.
Any other questions?
Okay. The idea of estimating pit depth using satellite imagery is a very interesting idea. And actually, the phenology response of green plants to pit depths, establishing that relationship would need lots of ground observations that you must have done. And I would just like to know how much is the agreement between the satellite-based estimates and the ground-based measurements. How accurate is that model?
So you ask the accuracy, or
Yeah.
so we have actually the monitoring areas. So for example, the peak depths, and the half data is for calculations, and the half data for the evaluations. And so this is the 90%. What to say? Yes. Something like that.
Any other questions? No? Okay. He will be here until 12 here in our division, so if anybody would like to discuss with him further, he'll stay here with us. So please join me in thanking him for an excellent seminar. And I would also like to announce that there will be another special SSD seminar on Friday to be given by Dr. Jacqueline Ashby, and she will be discussing about the gender strategy for the CPI.